I wanted to use Gauss's law to find the electric field of a spherical conductor. And you might think to yourself, didn't we just do this video? In fact, there were two the other day I had to watch. And the answer is not really. Because in the previous videos, I did deal with a spherical object, but I never really said anything about the nature of its makeup. But I did say that the charge was uniformly distributed throughout the sphere. That meant that anywhere in that sphere, if I took a little chunk of it, I would find some charge. And so what we now know, or what we can say further about that example, is that that spherical object that I dealt with that had charge distributed uniformly throughout it was an insulator. Because an insulator can have charge just within it that's not moving and be in equilibrium, where, as we learn in the end of chapter 6, if you have a spherical conductor, if you have a conductor and it's in equilibrium, it can't have like some charge inside of it floating around, because in order for it to get into equilibrium, the charge will distribute it along the surface. Furthermore, we learned that the electric field within that conductor has to be equal to 0. So what we're saying here is, in this case, right here, the electric field is 0, and we're saying that the charge that this conductor has all is sitting on the surface of the conductor. So in my made-up spherical conductor, I said it had a total charge of plus Q. And so that's what those positive signs are supposed to represent, plus 2 big Q sitting on the surface of the conductor. Now, we could actually use Gauss's law to prove to ourselves that the electric field inside of that conductor would have to be 0. If we did inside, and we did E dot dA equals Q enclosed over epsilon naught, well, I just said all the charge was on the surface, so if I took a little circle right here that represented my Gaussian surface, I can't put it, there's no charge in it because all the charge is on the surface. So this right-hand side of the equation is 0, which means that the electric field has to be 0. It's the only way to make that equation work. Now, if I look outside of the conductor, now outside I expect that there's electric field pointing out. This is the area vector. They're parallel to each other. So the electric field is parallel to the area vector, and the electric field is constant on that surface. And so I can simplify that integral a couple ways. The area, the surface area of my Gaussian surface is 4 pi little r squared. My charge enclosed is plus 2q over epsilon naught. My electric field ends up to be 1 over 4 pi epsilon naught 2q over r squared, which could be written as k times 2q over r squared. And so it's interesting to think about how this example varies from the example that we did with the insulating sphere, which at the time we didn't even know was an insulator maybe. That is, outside of the sphere, the electric fields will look the same. It's a 1 over r squared dependence, and it acts as if the 2q is located at the very center of the sphere. The difference is, if we look at a graph of the electric field versus the radius for this conductor, we actually would find that when we were within the conductor, the electric field would be 0. It's going to jump up to the value of K times 2Q over big R squared at the surface, and then it's going to look like 1 over R squared as we go further away. So this is sort of the area where it's different for the conductor. Remember, for the insulator, it was linearly increasing because we were going to be enclosing more and more charge. But we didn't have any charge inside the conductor, and so that's why the electric field looks like a little different. So that's an important thing to sort of grasp, and it's not often made explicit when you read something, but usually if it's a conductor, it'll say it's a conductor, but if it's any other kind of situation where the charge is distributed within the volume of the object, it's an insulator.